Imagine you need to know 7 things about your environment, all at the same time: temperature, humidity, air pressure, air quality, acceleration, rotation, magnetic heading. Now imagine wiring 7 separate sensors into your microcontroller with a dedicated data line for every single one. That's 14 pins minimum, 14 connections, 14 chances for a wiring error, 14 separate libraries fighting for CPU time. For a drone that weighs 250 grams, that's not engineering, that's chaos. And that's exactly the problem that most hardware developers hit when they try to build serious multi-sensor systems from scratch. So today, we're going to solve that problem by understanding one of the most elegant communication protocols in embedded electronics, I2C. And then we're going to look at how 7 professional-grade sensors can share a single communication line without ever stepping on each other's data. Let's start from the beginning. I2C, pronounced I²C, stands for Inter-Integrated Circuit. It was invented by Philips back in 1982, and the reason it's still everywhere in modern electronics is because it solved a fundamental problem. How do multiple chips talk to one controller using as few wires as possible? The answer is 2 wires. That's it, 2 wires. One is called SDA, serial data. This is the wire that actually carries your information back and forth. The other is called SCL, serial clock. This is the wire that keeps everyone synchronized, like a metronome that tells every chip on the bus exactly when to listen and when to speak. Your microcontroller, whether that's an Arduino, an STM32, an ESP32, or any modern processor, acts as the I2C master. Every sensor on the line is a slave. And here's where it gets interesting. Every slave device has a unique 7-bit address baked into its hardware. When the master wants to talk to a specific sensor, it broadcasts that address on the SDA line. Every chip on the bus hears that address, but only the chip whose address matches responds. Everyone else stays silent. It's like calling out a name in a crowded room. Only one person answers. This is called address-based communication, and it's the reason you can chain dozens of sensors onto 2 wires without any of them interfering. Now, let's get specific about what's actually happening electrically. Both SDA and SCL lines are pulled high by default through resistors connected to your supply voltage. When nothing is being transmitted, the bus is idle. Both lines sit at logic high. The master initiates a communication sequence by pulling SDA low while SCL stays high. This is called the start condition, and every slave on the bus recognizes it as "pay attention, something is coming." After the start condition, the master clocks out 8 bits. The first 7 bits are the target address. The 8th bit is a read or write flag, telling the target sensor whether the master wants to send data to it or receive data from it. The addressed sensor acknowledges by pulling SDA low during the next clock pulse. That's called the ACK bit, acknowledgement. Now the actual data transfer happens, 8 bits at a time with an ACK after every byte. When the master is done, it releases the SDA line high while SCL is still high. That's the stop condition, and the bus goes idle again. The whole sequence happens at speeds between 100 kilobits per second in standard mode, 400 kilobits in fast mode, and up to 3.4 megabits in high-speed mode. For sensor data, even standard mode is more than fast enough. Now here's something critical that every developer needs to understand: address conflicts. Because I2C addresses are fixed in hardware, you can never have 2 identical devices on the same bus at the same time. If you put 2 identical temperature sensors on one I2C line, both will try to respond to the same address simultaneously, and you'll get corrupted garbage data. This is why choosing sensors with unique addresses is absolutely non-negotiable when you're designing a multi-sensor system. Some chips offer address configuration pins that let you set one of a few possible addresses using a pull-up or pull-down resistor, but even that gives you maybe 2 or 4 options before you run out. So when an engineer designs a board with 7 sensors that all need to coexist on a single I2C bus, they have to be extraordinarily careful about chip selection. Every chip must have a unique address that doesn't conflict with any of the others. You also need to think about power. Each sensor needs stable, filtered power at the correct voltage. You need decoupling capacitors close to every chip. You need the pull-up resistors on SDA and SCL sized correctly for your bus capacitance and speed. You need trace routing that minimizes noise pickup, especially on a board destined for a drone, where motors are generating significant electromagnetic interference. And all of this needs to fit into the smallest possible footprint, because the engineers and pilots and researchers who need this data are not going to sacrifice payload for a sensor board that's bigger than it needs to be. Designing a 7-sensor I2C board from scratch that actually works reliably in the real world, that's not an afternoon project. That's weeks of schematic capture, PCB layout, validation, firmware development, and debugging. Most developers don't have that time, and honestly, they shouldn't have to spend it. This is the Multi-Nav Pro Plus Sensors module from RFOXiA, and every single problem we just talked about has already been solved for you. 7 professional-grade sensors, 1 I2C line, 24mm by 18mm. Let's go through what's on this board. Motion sensing is handled by the BMI 270 from Bosch Sensor Tech, a 6-axis IMU used in professional drones and industrial robotics that delivers high-speed, low-noise accelerometer and gyroscope data simultaneously. Magnetic heading comes from the TMAG 5273 from Texas Instruments, a precision 3-axis magnetometer that gives you true compass orientation for navigation and heading hold systems. Atmospheric pressure is measured by the LPS-22HH from ST Microelectronics, the same sensor family used in professional weather stations and altitude hold flight controllers. Temperature and humidity are captured by the MVH4003D from MEMS-Vision, delivering accurate environmental readings that matter for both data logging and calibrating your other sensors. And air quality, the ZMOD4510 from RNSS, a dedicated outdoor air quality sensor that detects ozone and nitrogen dioxide, the exact data profile needed for environmental monitoring networks. Every single one of these chips has a unique I2C address, 0 conflicts. The pull-up resistors are sized and placed, the decoupling capacitors are there, the PCB traces are routed for minimum noise, the power rails are filtered, the board is FCC certified. You connect SDA, SCL, power, and ground, and you start reading data. That's it. This module plugs directly into the full RFOXiA ecosystem, pairs with the BLE module to stream data wirelessly up to 5 kilometers, integrates with the RFOXiA Connect app for live visualization, and if you deploy it outdoors with GNSS validation, you earn daily rewards for contributing verified environmental data to the RFOXiA network. 7 sensors, 1 I2C line, $39. The engineering is already done. Go build something. Visit rfoxia.com and claim your $10 welcome credit today.